Hello everyone. My name is Trevor Hasty, and it's my pleasure to introduce Professor Nati Srebro today, because Professor Donahoe is out of town. So Professor Srebro is a professor at the Toyota Technological Institute at Chicago, and he has cross appointments in the University of Chicago's Department of Computer Science and the Committee on Computational and Applied Mathematics. He's also been a frequent visitor to the Simons Institute in Berkeley. He obtained his PhD from Massachusetts, from MIT, 2004, and was also a postdoc at the University of Toronto and a visiting scientist at IBM, and also an associate professor at Technion. So, Professor Srebro's research encompasses methodological statistics and computational aspects of machine learning, as well as related problems in optimization. Some of his significant contributions include work on learning wider Markov networks, introducing the use of nuclear norm for machine learning and matrix reconstruction, work on fast optimization techniques for machine learning, and the relationship between learning and optimization. His current interests include understanding deep learning through a detailed understanding of optimization, distributed and federated learning, algorithmic fairness, and practical adaptive data analysis. And some of that's the topic of the talk today. On a personal note, I've known Nati through my students, and one of my past students, Jason Lee, spent some time with him in the summer, and we were working on our matrix completion together and had some nice fast algorithms and thought we had some nice results. And then Jason came back from the summer and he said, "Oh, Professor Srebro's already done this, that's the next thing already." So hooked us. So I got quite used to hearing the story. And one of my present students, Elena, is working on a project, and as a result of things we were doing, we needed a weighted SVD where each observation has weights. And she came up with a nice, simple iterative algorithm for doing that. And guess what? Professor Srebro had done it first. So I'm looking forward to this talk because I'll probably find out some more things that Professor Srebro has done that I was thinking of doing. You're welcome.
Thank you. Thank you. And I should say that the iterative SVD, I think, I discovered later, I think, was also sort of done first, also with, and to some extent, but yeah. Okay, thanks for the introduction. And I should say that this is joint work both with Jason Lee. Is this working? Oh, this is other one working. Okay. Any other microphones? Somebody, whoa! I broke your microphone. Wait. Do you know how to figure? What is this? How did I break it? This is just for amplification. Can you hear me in the back? If you can hear me in the back row, can you raise your hand? Yeah, good. I don't think I need this. Is that okay? I promise to speak loud. Oh, it's fixed? Okay, good. Okay. No. Okay. Now you can really hear me. So I feel like in a press conference, I have two. I can take more. I have two more pockets. Right. Okay, so I should say this is what I'm going to be talking about today. So about essentially my view of deep learning, at least the first half, and then maybe go into some more specific current work. And this is work with a bunch of co-authors, including Jason Lee that Trevor mentioned. Mostly the main kind of contributors or Benem Naishbur was a student at TTI, and Surya Gunasakar, who's a postdoc at TTI, and Blake Woodworth is currently kind of picking up the torch as a student at TTI working on this, and also Jason and Daniel Sudri, the Technion, and many others. Now, I actually was in a bit of I wasn't sure what to do with this talk, so I was actually here, maybe even in this room, I don't remember, only a few months ago, talking about inductive bias and optimization in deep learning, or maybe the title was a bit different. And I'm not sure how much to repeat myself. I mean, that would be boring, at least to me, and how much to talk about other things. I'm just curious, how many of you have been either in my talk here or heard this talk or some version of it or this topic before from me? Okay. So good. So some of you. So what I'm going to try to do in order to, so we'll see how things go. So feel free to kind of either nod with your hand, with your head if I'm going kind of too slow, or have really glazed looks if you want me to kind of slow down, and I'll try to adjust based on that. What I'm hoping is really to give, I don't want to exactly repeat because that would be, at least for me, be a bit boring. But I will try to, in the first half of the talk, and we'll see what half means, would go over really foundations, my view of deep learning and how the role optimization plays there. And then in the second half, and again, we'll see what half means, talk about some recent work, mostly talking about how everything I talked about in the first half relates to recent work on the tangent kernel. Okay, so let's start though with, do I have do I have a clicker of some sort or no? Okay, I'll just use, in that case, can I, no, I guess I'm stuck here. Okay, so is there at least a laser pointer? Nothing? Oh, okay. I thought this is a technologically advanced university. Okay, so the kind of classic view of deep learning, of learning with a neural net, is fairly straightforward. I mean, what's a neural net? It's just it's a model class. It defines some class of functions, what I can represent with that class of functions, and it's not very different from many other types of learning approaches where you define a model and then just fit the model and then try to generalize by whatever predictions you get from the model. And viewed this way, really there are three basic questions we should ask, which are, what is the capacity of this model, right? We want the model to constrain us in some way so that we can have hope of generalizing. Another way of asking basically the same question is, how many samples do we need in order to be able to fit the model, right? If the model is the number of sample scales with the capacity. What is the expressive power of this model? Like, what can we actually represent with it? Can we actually represent the type of things we want to capture? And then we also have to worry a bit about computation. How difficult is it to do computation on this model? And at least if I was giving this talk several years ago, this was definitely how I would view deep learning. And we have answers to many of these questions. So in terms of the capacity of this model class, of things you can represent with a neural net with specific architecture, I don't want to go into details, but roughly speaking, we know kind of the answer. And the capacity roughly corresponds to the number of parameters. And we can formalize it a bit more. So in a fully connected network, this is at least linear, roughly linear in the number of edges, maybe a tiny bit more than linear. And you can play all, with all. If you have infinite precision with certain activation functions, maybe it's a bit more, but we know the answer. And roughly speaking, at least for the purpose of this talk, you can think of it as just the number of parameters. Good, so we understand the capacity, and now the question is, what's the expressive power? How useful are these things? What type of functions can we capture with neural net? And so one line of results coming from approximation theory tells us that neural nets have great expressive power because they can represent any continuous function, right? So any continuous function, and I can approximate arbitrarily well with a neural net. And again, what do I mean by continuous? What do I mean by approximate? I mean, there's some details here, but the rough thing is I can capture essentially any function. Okay? So this is great because that means that we can learn everything. But of course, we have to be conscientious of the capacity because in order to learn, we have to limit our capacity. So we have to learn only things with a bounded number of units. And in order to represent any function, we need a huge network, right? We need a network that is exponential, and the size of the network has to grow exponential in dimensionality. So this type of answer is not really useful to us, right? Because what we really care about is not what can represent with a neural net, but what can represent with neural networks that are relatively small, neural networks with a small number of parameters. And still here, we have lots of answers, and there's been much of the, if you look at people explaining why do neural nets work well, there's been lots of work on this and all kinds of interesting things you can capture with neural net. Okay, all kinds of things that you cannot capture with, say, linear models, right? The original motivation, or one of the original motivations for introducing neural nets, or as they call it, time multilayer perceptrons, was because they can capture things like parities, which you cannot capture with the linear model. And since then, if you look at vision, if you ask a vision researcher, he'll tell you how neural nets are great because even with relatively small neural nets, you can really capture all kinds of visual phenomena. You have low-level features in the bottom and mid-level features and high-level features, and you can really, this formalism captures many things we want to capture. So the expressive power is very compelling, but really, we don't need completely these answers because if you go to a complexity theorist, he'll tell you that actually even small neural nets can capture everything. What do we mean by everything? They can at least capture anything you can compute efficiently. So any function you can compute in time t, you can capture with a neural net of size roughly t. Now note that this is not the training time. This is the time to actually compute the prediction. Okay? And so, and I would argue that you'd only want to learn at all functions that you can actually compute efficiently. Because if you can't compute it efficiently, then your problem is not a learning problem, right? Even if somebody tells you the right thing, right? About the goal of learning is to be able to figure out the right thing from examples. But forget figuring it out from examples. Even if I told you the right thing, if you can't actually compute it efficiently, then what are you going to do with it? Okay? So in any case, we only care about things we can compute efficiently, and anything we can compute efficiently, we can also represent with a relatively small network. So in that sense, we are actually back to saying that we can actually say that neural networks really are a universal learner. You can represent anything you'd want to represent with a reasonably sized network that you can then train using a number of samples. It's only scales roughly linearly with the time it would take you to compute, which is actually fairly sensible. The problem, so from this view, neural networks are great. The problem we run into is, of course, the optimization problem, the computational problem. So in order to actually learn anything, to say that you can learn everything here, you have to be able to actually fit data to a network. So take a network and find the weights or whatever that best fit the data you have. And this problem is, as we know, is computationally intractable. And it's computationally intractable even for tiny networks. So, okay, so if you have a network with a single node, okay, that's a linear model, that you can fit tractably, at least if your loss is convex. But once you have anything that's slightly more complicated than that, even a network with 2 hidden units, cannot, this is really the simplest possible thing that's not linear, okay? Then already here, the problem of taking data and finding the best fit for the weights that best fit the data, or even just finding weights that fit the data perfectly if they exist. So even if you assume there's no error, okay, is intractable here. It's NP hard. Okay, so in that sense, things seem pretty lost. I mean, it's okay. It would have been great if we could do it, but we provably cannot do it. But it's all lost. So you can say, well, maybe if I make if I use a model that's bigger, or I make do some other trick, like for example, maybe if I can fit my data perfectly, if I assume that my data is actually captured in a very small network, and I use a much larger network to learn it, right? So this is what we say. We use more parameters than we need in order to make the computation easier. Okay, so that's a sensible approach, and you can think maybe this would work. Maybe actually saying that you can fit data with a network is a useful thing because we can prove that if we use a sufficiently large network, we'll actually be able to learn. Unfortunately, I have bad news for you, and even that's not going to work. So we can have very, very strong negative results here, and I should emphasize none of these results are mine. That tell us that we're basically doomed. That no method, even if you're going to fit a much, much bigger network, no matter what you're going to do, okay, there is no method that's going to guarantee to learn just based on the assumption that you can fit the data or that you can fit the distribution perfectly, fit your function perfectly, even using a relatively small network. Okay, more than 2 hidden units. You need a super constant number of units, a logarithmic number of units, but still very small number of hidden units, 1 hidden layer. And even if you can fit it perfectly without even any errors, right? So if you make the assumption you can fit your data perfectly with a network with a very small number of units, and you're going to try to learn it with a much, much, much bigger network, or a combination of networks, or any other more sophisticated network, that's not going to work. Okay? So what's going on here? So this basically, what I'm telling you now is that deep learning doesn't work. Okay? That we have these theoretical results that tell us, and we can prove to you that deep learning doesn't work. Even if you can represent your function with a small network, no matter what you do, you're not going to be able to guarantee that you can learn it. Okay, so however, I'm curious, how many people here have actually trained a deep network? You actually ran code. Okay. Did it work? Yeah, it did work. Okay. So what's going on here? Okay. What? It worked well even, maybe. I don't know, for sometimes. Okay. So deep learning obviously does work, right? It worked for you, and it works for, inside the, where's my phone now? I don't know, I have too many microphones here. Probably the microphone has a deep network these days also. I think my phone has lots of them. So what's going on here? In practice, we see that deep learning actually does work. So why does it work? Okay? Well, remember that these harness results are worst case results. They say that just based on the assumption that we can perfectly fit the data, that there exists a network that perfectly fit the data, that by itself is not sufficient in order to guarantee that, that any optimization algorithm will work. Okay, there's no optimization algorithm, no learning algorithm that's guaranteed to work just based on this assumption that there is a perfect fit for the data. Okay? On the other hand, we see that the problems we actually care about, we can actually fit the data. So what's going on here? It seems that all the problems that we care about, many of the problems we care about, many natural problems, have some kind of property that actually makes local search work. Okay? And this is maybe the biggest mystery of deep learning. I should say this is not the mystery I'm going to talk about today. But this is, I feel compelled to talk about it every time, especially in a class that I talk about deep learning. This is really the big mystery of deep learning. How come local search, a really simple search, actually succeeds even though we know that in the worst case it's not going to work? What is special about the problems we have that makes local search work? Okay? And I would argue that we don't have even the slightest idea what this magic property is. What is this property that of problems we actually encounter, like problems in vision or in language, that makes them learnable by a neural net? The only thing I can tell you, following these negative results, is what this property is not. This magic property is not that there exists that you can actually explain the data using a neural net. It's not that there exists some neural net that actually handles the data. So if you go to a vision researcher and ask the vision researcher, I'm not going to pick on anybody here, why is neural network good for vision? And they tell you, okay, neural networks is good for vision because many visual phenomena can be explained very well by low-level features and mid-level features and high-level features. And look, neural networks really capture vision very well. All he's answering is this question about expressive power. All he's telling you is that there exists a good network with small error. But we know, that's the only thing I do know, that property by itself does not explain why local search actually succeeds in learning. Okay? And so again, so I have no idea what this magic property, so this explanation provides absolutely zero explanation for why neural networks work. Because we already know that actually any function that we could conceivably care about, any function we can compute efficiently, is representable by a neural net. We already know that. I don't need you to explain to me why your specific visual phenomena is explained by neural nets. In providing this explanation, you're not providing any evidence towards the real mystery, which is why local search works. Okay? And so again, I don't know what this magic property is. I really hope to find out, or that somebody else would find out. But I know what it's not. Okay, so if I was giving this talk 5 years ago or so, I'd probably focus on this. And this is actually where my interest in deep learning started. But what I'm actually going to talk about today is something else, because as I said, I have no idea what this magic property is. So I just don't have a talk to give about it. Otherwise, I would love to give it. What I'm going to talk about is how actually this view of deep learning, it probably doesn't actually capture at all what's happening in deep learning. In particular, under this view, really what's controlling deep learning is this model class, the class of functions you can represent with the networks we have. In particular, the capacity is given by the number of parameters. But it seems like that's actually not the case at all. Okay? In particular, we have, we first observed it in 2014 in a paper with Benem Neishabur and Mioka, where we looked at what happens when you train larger and larger networks that have more and more parameters. And we saw that two surprising things. One is that you actually, even if you have a lot of parameters, many more parameters than the amount of data, you generalize well, and actually generalize better when you over-parameterize even more. Okay, so this slide, which maybe if you've already seen. I've shown it in so many talks that it's now featured in other people's talks. This is Peter Bartlett giving a talk explaining how what we saw in 2014, they already saw in 1996. Okay, so a long time ago. So actually, and what both of us are showing here is how you're fitting networks with way, way more weights than parameter. In our case, at least, it's without any form of explicit regularization. You're just fitting the network. And two surprising things happen again. One is that when I have, like several thousand more parameters than examples, but if I read Trevor's book, then Trevor would tell me I should not be getting any type of generalization there. I'm doing something really horrible. It's working great. And more than that, if I have more and more and more parameters, if I have, what, sorry, you wouldn't say that? No? That's right. But I'm not regularizing. It's without any regularization. Okay, so, okay. We'll get to that. Okay. And then the other thing is, again, so when I have more parameters, I'm learning even better. So what's going on here? So, I mean, and the other evidence here is that really the networks we're using in practice, the networks that drive this phone, are very, very large. They're so large that said we can fit everything. We can fit also, there are other papers showing that you can fit junk labels. You can fit anything. So if you can fit anything, and the networks are so large, maybe those approximation theory results are actually correct. That really we should think of neural networks as models that can present any function. But in that case, what we're doing doesn't make any sense because we're finding a function that minimizes the error in our data. It's very easy to find a function that minimizes the error in our data. I'll just have a function that returns the training labels on the training points and 0 or whatever, everything else. Okay? Just memorize the training points and not generalize at all. So just saying that I'm searching over the space of all functions for something that fits the data is completely stupid. Yet this works great. And the reason is, it seems that what we're doing is, it's not that we're going to find that function. When you're training a deep network, you're not actually going to find this function that's just memorizes the data and is 0 everywhere else. But rather, what's happening, you're searching in the space of all function. You're searching in a particular way, and your search magically brings you to a solution that's actually good. Okay? So you can think of it roughly like this. You're searching over a huge optimization landscape, right? You have many, many parameters. And there are many global minima. Okay, all the global minima, this is your loss function. There are many global minima of the loss. Okay? What's the value of the loss of these global minima? For your training loss? 0. So I know they're global minima because the loss is not negative. So I have tons of places 0. So these are the oceans. You can think of it if you have tons of oceans. I'm going to start optimizing somewhere which is not an ocean, like here. Okay? And I'm going to start optimizing, and I'm going to do some local search. Which global minima am I going to? So suppose I get to a global minima. There's also an issue I might get stuck in a local minima. But suppose I get to a global minima. Which global minima am I going to get to? I'm not going to get to a global minima in the middle of the ocean. I'm going to get to a global minima on the beach. In particular, if I start optimizing here, I'm probably going to get to the San Francisco Bay or something like that, global minima there. If I start optimizing in Boston, then I'm going to get to, I don't know, somewhere in the Atlantic. Okay? So what's happening is the optimization algorithm drives us to a specific global minima. And that specific global minima has special properties. In particular, it's kind of close to where we started in some sense. And really, those special properties is what drives generalization. Okay? Now, the interesting thing is not what happens when I start optimizing here or in Boston, but what happens if I start optimizing in Chicago. Okay, so if I start doing local search from Chicago, where am I going to get? What? The Gulf. I might get to the Gulf. So I might get to the Gulf of Mexico. I might get to the St. Lawrence. Okay. I might actually get with some effort to the Atlantic seaboard. I mean, that's because Chicago is so flat. The rivers. I mean, I really don't know because the rivers actually flow backwards in Chicago, right? I mean, it's that. I'm serious. Okay, it's that flat. So now, depending on kind of where your optimization algorithm prefers going, you're going to go to different places. Okay. If you have an optimization algorithm that likes going south, in some sense, you're going to get to the Gulf of Mexico. If you're going to get an optimization algorithm that likes, flowing on, cold rivers, you're going to get to the St. Lawrence. Okay? And so the geometry of your optimization algorithm, which directions it likes going, is going to determine what kind of special solution you're going to get. Okay? And so, so in particular, if I'm claiming that all the inductive bias is coming just from an optimization algorithm, because my model class is anyway all functions, then if I change my optimization algorithm, then I'm going to completely change what kind of thing the learning algorithm is looking at, what the inductive bias is, and what the generalization properties are. And the thing is that in high dimensions, all the points are like Chicago. Okay, so in high dimensions, you can really get, just by going down, you can get from any point pretty much to any other point, because you have tons of different directions you can go down in. Okay, 2 dimensions is very boring that way. Okay. And you can see this in practice. If you change the optimization algorithm without changing the model, just changing the optimization algorithm, you get to completely different generalization characteristics. And I'll show some brief examples here. Here is an example. We train two different models, the same model, two different optimization algorithms. Doesn't matter what they are, a blue algorithm and a red algorithm. Both algorithms find the global minima of the training objective on your left. How do I know that it's a global minima? It's 0. Okay, I found the point with 0 error, so it's definitely a global minima. So both of them, in terms of optimization, are doing their job. They're finding global minima. The blue one may be a bit faster than the red one. That's less important to me. But now when I go to the generalization error on the right, the test error, okay, I see that the blue algorithm actually found much better global minima than the red algorithm. Now what does it mean that it's much better? In terms of what the algorithm was told to do, which is minimize the training error, it's just as good. Okay? It's a global minima. How can you have a better global minima? But in terms of some unspecified property that I did not explicitly ask the algorithm to do, it's actually doing much better. It's in some sense has a better inductive bias. Okay? Another example is here I'm comparing again two optimization algorithms. In this case it's SGD and Adam, but it doesn't matter. It's a red algorithm and blue algorithm. In terms of optimization, the red algorithm is a bit better. It's faster. Okay? They both are going, if I continue far enough, they're both going to get to the same training error. But if you look at the test error, I see that the blue algorithm is actually much better. It took it longer, but it found a much better global minima. Again, better in this thing, I'm being completely unfair to the algorithm here, because I'm measuring the algorithm on something I didn't tell it to do, okay, which is find a good, whatever that means, global minima that's going to generalize well. So there's some hidden property here of the network, okay, that the algorithm is biasing towards. So that means if you look at your typical deep learning paper, we focus a lot on the model, right? We suggest a new model class with all kinds of fancy residual connections and convolutional connections and all kinds of other really fancy stuff, okay? And we focus on why this model is a good model, okay? But what I'm telling you is that this model, it doesn't really matter because anyway, it's a model of all functions. Okay? And then the optimization is almost an afterthought. We say, how do we train the model? Well, we just minimize the loss. How we do it? I mean, you use the standard stuff. It's an appendix. Okay? If we're lucky, it's an appendix. More likely, it's not even there. And it's maybe in the source code and probably not even there. Okay? And what I'm saying now is that everything, all the learning, everything that gives me generalization, that determines the inductive bias, everything is in this, how we actually do the optimization. Okay? Okay, so maybe this seemed a bit kind of abstract. What I want to do is try to demonstrate exactly this phenomena in the simplest possible deep network that I know of. In particular, it's a problem, the only problem maybe that I understand somewhat well, which is matrix completion. Okay? Okay, so what are we doing in a matrix completion problem? So matrix completion problem, we have partially observed metrics. And you can think of it as maybe movie ratings, right? Users in movies or whatever you want. I mean, you observe part of the entries. For some of the users, some of their movie ratings. And what I want is to complete the unobserved entries. Okay? How am I going to solve this problem? I'm just going to write it as an optimization problem of find a matrix X, okay, that minimizes the error on the observed entries. Okay, and then I'm going to use this matrix X to complete the unobserved entries. Does this method make sense? No. Why not? How would you, what's a global minima of this optimization problem? Y, or like complete Y is only part of the entries. So you complete the observed entries and put 0 everywhere else, or put 50 everywhere else, or write the Fibonacci sequence everywhere else. There's tons of global minima, but none of them make any, not none, but the global minima don't make any sense. They're not gonna, I don't expect that if I have X that completes the observed entries and has the Fibonacci sequence in unobserved entries, that is a global minima. It's completely legitimate global minima of this optimization problem. It's likely not going to generalize, no matter what these ratings came from. Okay, so what are we going to do? We're going to take the deep learning approach. We have an optimization problem that doesn't make any sense. And at least it's convex. Okay, this is at least a convex optimization problem that we can solve easily. Right? It's just a it's even simpler than linear regression. And we're going to take the simple convex optimization problem that doesn't make any sense. Why does it not make any sense? Because it has too many parameters, right? There's more parameters here than data points. And we're going to have even more parameters, and we're going to make it non-convex. Okay, right? This is exactly the deep learning approach. So now I'm going to write X as U times V. Okay? And X and U times V are full dimensional. So if X is n by, n by n here, then U and V, each one of them is also n. Okay? So I have twice as many parameters. So I have too many parameters. And this optimization problem is non-convex now. Okay? But I'm not afraid about non-convexity because I do deep learning. is that this problem is just as nonsensical as the problem we had before, because it's the same optimization problem, right? It didn't actually change the model class. Any matrix x I can present as u times v. Okay? So when they do this optimization over u and v, I still get all the same global minima that don't make any sense. I can still have a solution in which I complete the observed entries and put the Fibonacci sequence everywhere else, right? I'll just set u to this matrix and v to the identity. Or I can do it in a bunch of other ways. Okay? So this optimization problem completely doesn't make sense, but we're going to do what we do in deep learning, which is solve this optimization problem that has too many parameters, is non-convex, solve it using gradient descent, right? That's what we do. Okay, so what happens? Okay, so what we're going to compare here is actually solving it by gradient descent on u and v, which is the deep learning approach, and solving it just by gradient descent on x. Okay, and what we get is this following. So what I'm showing you here is for gradient descent on x and, sorry, descent on w. W and x are the same thing on this slide. Gradient descent on w. I really should change this. This is gradient descent on w, not on x. Gradient descent on w and gradient descent on u and v. So what I'm showing you is the training error, how well I fit the observed entries. So great, I got zero error. That's not surprising, right? I have way too many parameters. It's very easy to get zero error. So both methods actually fit the observed entries. But the interesting thing is, what is my error on the unobserved entries? So the way I'm showing it here, I guess, is the error on all the average error over the entire matrix, including the unobserved entries. So if I do gradient descent on W, then surprise, surprise, it doesn't generalize. I basically do, the only reason I have 70% and not 100% error here is because I observed 30% of the entries. On the entries that I didn't observe, I just didn't do anything. Okay, that's not surprising. The surprising thing is that if I do gradient descent on U, which doesn't make any sense, actually, it works pretty well. Okay? It gets me, 10% error, which is very non-trivial. Now, the thing is, now let's see what happens if I change my optimization algorithm. So this is actually gradient descent with exact line search. It's actually a good optimization procedure. Let's instead do gradient descent with small step size. This is a worse optimization procedure, right? So it's going to take me much longer to optimize. If I'm putting my optimization hat on, or if somebody who does optimization would come in the room, they'd yell at me, why am I, use line search. Line search is great. Why are you doing this small step size business? Okay? But if we look in terms of generalization, in terms of the test error, it's actually much better. Okay? Just as we saw before when we switched, say, from SGD to Atom. Okay? So again, so there's two things here. One is the changing optimization algorithm actually makes a big difference, but also the fact that it works at all in the first place. Why am I getting generalization here? This doesn't really make any sense. Where is the generalization coming from? Okay, so in this specific case, we actually kind of understand what's going on. And we kind of understand it in the sense that what we know is that what gradient descent is actually doing here, it's finding a global minima, but it's not just finding any global minima. It's finding a global minimum. Among all the global minima, it's biased towards a global minima that minimizes the nuclear norm or trace norm. Okay, so finding the matrix W with minimum nuclear norm. And again, I really apologize. I keep not fixing this. X and W are the same. When I write X, I sometimes, I just switched from W to X. This is the optimization variable I'm searching over. Where was I? Okay. And now, we can now break the explanation here to two parts. One is, what is the optimization algorithm actually doing? The optimization algorithm, it's not just finding a global minima. That's the easy part. It's finding a global minima that minimizes the nuclear norm. And now you can ask me, so now I identified what is the inductive bias here. The inductive bias is small nuclear norm. So now I'm not finding any beach. I'm finding the beach which is smallest in nuclear norm to where I started, which is, I have to start here close to the origin. And the second thing is I can say, is minimum nuclear norm a good inductive bias? Okay? And the answer is yes. We already know that we knew before that if your matrix is approximately low rank, your target is approximately low rank, then actually the small nuclear norm solution, minimum nuclear norm solution would actually get you, would generalize well, which is what's going on here. Okay? I can also actually know what the inductive bias of doing gradient descent over x is, or gradient descent over x, which is w. What I get there is a minimum Frobenius norm solution, and that's really bad here. Minimum Frobenius norm solution would mean fit the observed entries and don't touch the remaining entries. That's not going to generalize. Okay? So both optimization algorithms, a priori, the optimization algorithms, each one has a very, optimization algorithm meaning gradient descent over W and gradient descent over XY, over U and V. Each one of them has an inductive bias which you can describe, Frobenius norm and nuclear norm. And it's just that the nuclear norm inductive bias is a much better inductive bias for the type of matrices we expect to get. Okay, so in this case, we understood what's going on here. And I should say that the picture I gave here is too overly simplistic. We don't, when I say we understand this, we only sort of understand this. This is Argot. There's a follow-up paper by Tengi Ma, who's here with the students that got even closer to understanding what's going on here. There's still lots of gaps, and you're welcome to read about that or look at some other of my talks, but I'm not going to go into this here. Yes? Right, so that's very important. Okay, so thanks. That's a perfect question to ask now. This is also sensitive to initialization. I'm not showing you here, but in order to get a nuclear norm solution, you have to start infinitesimally close to 0. So you cannot initialize at 0, because if you initialize u and v to 0, that's a saddle point. You're not going to move anywhere. But the nuclear norm is going to be obtained only when initialization is extremely close to 0. And we'll return to that later. That's going to be a very important point in the second half of the talk. Okay, so what's going on here? The main thing that happened here is not so much the optimization algorithm itself, but what parameterization I used. So I looked here at the space of matrices, the space of all matrices actually, and the special thing here is that I parameterized them in a special way, as a matrix factorization, as u times v. And what happened is they optimized in this parameter space, and maybe in this parameter space I had fairly simple geometry and fairly simple inductive bias, but once I mapped it to the predictor space, in this case the space of matrices, I actually got very complex, very structured, very rich inductive bias, namely the nuclear norm, which is actually good for generalization. Okay? And we see this happening more generally. And these are, I'll show you sequence of examples where we're really optimizing in the space of, in some sense, all functions, but we're parameterizing them in a particular way, and this parameterization is inducing a search geometry which is leading us to very rich inductive bias. So again, the first example is this matrix completion example. In this case, the class of all functions is the class of all matrices, right? Our functions are just matrices. Okay? So we're not constraining the model class at all. What's special is how we're searching within this model class. Remember, that's what we talked about before and what we want to see. Another example is linear convolutional networks. So linear convolutional network is a deep network with a convolution at each layer, a full width convolution, but all the activations are linear. If all the activations are linear, it doesn't matter how many convolutions you have there. At the end of the day, you're just representing a linear mapping from input to output. So the model class here is just all linear functions from input to output. So this is just a very overcomplicated representation of linear predictors. So what we're doing when we're learning with linear convolutional networks is just doing linear prediction. But we're doing linear prediction under some very convoluted parameterization. And now we're asking what happens if I actually do gradient descent on this convoluted representation. Okay? So what I get in this case, I'm going to find a linear predictor, but which linear predictor I'm going to be biased to? And without going into the details, roughly speaking, I'm going to be biased to a linear predictor that minimizes a sparsely inducing penalty in the Fourier, on the Fourier transform, in the frequency domain. Okay? So what I get is things that look like this. This is on the top. This is what I get with a fully connected network, which minimizes corresponds to just minimizing the L2 norm of the predictor itself. But if I use a convolutional network, and again, I'm not constraining here what I'm optimizing. This is not a bias introduced by the model class itself. Even though it's a convolutional network, it can represent anything. But when I do that, I get things that become more sparser and sparser in the frequency domain. This is with depth 2, and with depth 5, I get extreme sparsity in the frequency domain. Okay? So again, I have a model class here, which is all functions. In this case, all functions is all linear predictors. I'm parameterizing them in a complicated way and doing gradient descent on this parameterization, and that induces very rich inductive bias on the predictors, namely given by sparsity in the frequency domain. Okay? A last example, and also here there's some details I'd rather not go into, is now we're really talking about, but I have the answer here. We're supposed to have an answer. Okay, sorry. So now we're talking about really all functions. Okay, and we're going to represent all functions by infinite width ReLU networks. So one hidden layer, one hidden ReLU layer. With enough units, you can approximate all functions. So you're really representing all functions here. And so searching over this infinite dimensional ReLU networks, again, doesn't constrain your function class at all. What constrains it is where what's the geometry within this function class. And what we can uncover here, at least if we use weight decay, and I believe this is true also without weight decay, but this is still something we're figuring out now, is something that also makes sense. It turns out that what's going on here is, at least in one dimension, what you're essentially doing by doing that is minimizing the integral of the absolute value of the second derivative of your function. So you're finding a function fits the data and minimizes this smoothness measure, which is kind of a second order total variation. Okay? This is a very natural smoothness measure, right? I mean, you want something that you want to fit the data with something that's smooth. In fact, if you're designing some kind of non-parametric learning procedure and wanted to fit the data but get some kind of regularization, this would be something very sensible to do. Right? What we're seeing here is that we didn't actually program it into the system. We didn't tell the system regularize in this with this smoothness penalty, but rather all we said is use a two-layer infinite width Rayleigh network, and implicitly that's actually what's happening. Again, so this is the bias induced by this specific representation of all functions. In higher dimensions, you get this a fairly recent result. You get something very similar, but now you have to take the integral of the absolute value of the d plus 1 order, if you dimension d derivative of the Radon transform of the function. And we can still at least write it down. There's roughly that at least. Okay, the point is in all of these examples, what we had is our model class is all functions, as we said before, and so just limiting the function class doesn't limit at all. Everything comes from an optimization. But this is not to say that so at the beginning it said, oh, this architecture, who cares about the architecture? Care only about the optimization procedure, because the architecture just specifies the space of all functions. What the architecture specifies is this parameterization. So we do care about the architecture, but it's not that we care about the architecture in defining a model class. We care about the architecture in how the architecture defines a specific parameterization, and through that defines the geometry on the space of all functions. Okay, this is a geometry by which we're actually searching over all these functions. Okay, this was the longer half. So I have half an hour, you said, or so now? That'll be, according to, you said, I have an hour and 10 minutes. So, okay, good. So, okay, so this is a good, so what we're trying, so following this, in order to understand deep learning, what we're trying to do, and this is in a sequence of papers in our group, is really trying to understand this connection between the optimization algorithm and the parameterization and the resulting inductive bias you get in function space induced by this local search. Okay, this is going to be a good, if there are questions so far, maybe this is a good time to take some questions before we move on to the second half. Okay, yes?
So all the optimization you showed before, you always use gradient descent.
Okay, and what I showed here is gradient descent, but we started actually by asking what happens if you have different optimization procedures. So if you use, for example, we have looked at what happens if you use coordinate descent or steepest descent with respect to a general norm. For example, in the examples I started with, I actually, instead of gradient descent, I used the Adam, which is a variant of Adagrad, and I used this path SGD, which is actually approximate steepest descent with respect to some other local norm. Okay, so we did definitely investigate also what happens if you change the optimization algorithm on the parameterization, but in more recently, like in the past year or so, I think I've at least shifted my attention mostly to look at the parameterization, because it seems that these changes in optimization algorithm do make a difference, okay, as we saw in the beginning. And also for us, it was very useful to go through this and say, okay, build this mapping of optimization algorithm, inductive bias, optimization algorithm, inductive bias. But it seems to me that roughly, okay, I don't have it here, but roughly you can think of it this way. You have this picture, inside parameter space, your inductive bias inside parameter space is controlled by your choice of optimization algorithm. And that will give you all kinds of, roughly speaking, instead of this like ellipsoid, might give you something with a different shape in parameter space. That does influence things, but to get really rich things, and the much more important thing is this mapping from parameter space to function space. Okay, this parameterization, which completely like distorts, if you think of it in terms of geometry inside the search geometry, changing from like gradient descent to coordinate descent slightly distorts the geometry, but changing the parameterization completely warps the geometry. Okay, is that so? We've been focusing attention mostly on that. Yes. I could, but I think I'd rather not because I want to talk about other things. I mean, you can give a whole talk about that. So instead I'll direct you to our paper on that. There's a paper called Inductive Bias of Linear Convolutional Networks. Okay. Yes.
So, what do you think of the argument that maybe we should just explicitly write down the regularized?
Okay. Excellent question. So, you can ask, why rely on this implicit regularization? Why not just regularize directly? In particular, I just showed you how to solve matrix completion by doing completely by fitting this huge model without any regularization. Why don't I just explicitly find a matrix, minimize the loss plus the nuclear norm? In fact, that would be a much better way for doing matrix completion if I assume the reality is approximately low rank. the thing is that what the point of view that I'm coming to this is that in deep learning, we don't know what this implied regularizer is. What we have something that works, okay? And we're trying to understand why does it work. So we're trying to understand what is this implied regularizer. After we understand what it is, then we can maybe introduce it explicitly, okay? Or my guess is maybe it's going to be too complicated to actually write down explicitly, but at least we understand what it is, and we can tweak it either more directly by changing local search or by adding explicit terms as well. Okay? But definitely the thinking process here is not I'm starting with a regularizer. I know what it is. I can either choose to put it directly or have an optimization algorithm that can implicitly, but rather I start an optimization algorithm. I want to understand what it does because it works, and then maybe tweak it. Yes?
Once you acknowledge there's an implicit regularizer, it's not obvious that you always want to train down to zero training.
Yeah, so that's true. And that also, right, so that opens a whole nut and a whole other can of worms. So in what I showed today, we always train to zero training error, and we can do it because we're way over parameterized. And now Trevor is asking, do I actually want to do that, or do I actually want to treat it as an actual regularizer, as a student just bias, and balance between the regularizer and the fit? Maybe not. I don't think it's clear. But you're right. In order to be able to do that, we kind of need to understand what the regularizer is, because all these methods are really getting, and we'll see this later on, they're really getting, the regularizer kicks in only when you're really deep in the zero error regime. And so in order to be able to do this balance, I kind of need to understand what the implied regularizer is. Okay, so let's shift gears to the second talk, and what some of you might be asking. Well, I understood you heard several talks about the tangent kernel, and might be saying, okay, we completely understand deep learning. It's all just the NTK, okay? Doesn't just the NTK explain everything? Okay, the optimization, what we get. Okay, okay. So let's think about how the NTK relates to all this implicit bias stuff. Because remember, point of view is that the implicit bias is everything, and definitely, if you think in terms of NTK, the NTK kind of in all the work on neural tangent kernel, it's all in this over-parameterized regime, which you have to rely on the implicit bias. Okay, so what is brief reminder? What are we talking about when we talk about the tangent kernel? Really just a first-order Taylor approximation. If I look, I can look at a first-order Taylor approximation of my model. So my model with parameters W and input X. I take it first-order Taylor approximation with respect to W about the initial point, initialization W naught. So this is first-order approximation, and it's just a linear function of W. So you can think of it as some kind of linear model with the feature space given by phi, which is just the gradient of the model with respect to W, because that's what comes up in the Taylor approximation. And if you prefer, instead of thinking about a feature space, think about the implied kernel. I mean, any linear model with some feature space, you can also just kernelize it and think in terms of the implied kernel, which is given here. And so this is always, I can always write this Taylor expansion, but it's particularly useful when we're in this kernel regime. And when is this kernel regime? The kernel regime is when this feature map phi, or the kernel k, doesn't change throughout optimization. So in other words, the gradient remains fixed. I'm essentially throughout optimization still in the regime where this linear approximation is valid, right? So for any model, essentially, I have about any point, I can talk about the linear approximation. The question is how far from W naught is it valid? And if it's far all the way out to where we get an optimization, then I can just think about this linear approximation and forget about everything else, okay? Okay, so if we are in fact in this kernel regime, and we can just approximate the model using this first order approximation, then what can we say about inductive bias? Well, in that case, all we're doing is training a linear model using gradient descent. And we know exactly what the inductive bias of training a linear model using gradient descent is, at least with the squared loss or many other losses. What we'll get is just the minimum norm solution in that space. Okay, so in other words, the predictor, the minimum RKHS solution and the corresponding RKHS. Okay, so I can tell you exactly what the inductive bias Yes. Okay. Now, this is a bit disappointing because that means that all we're doing with deep learning, the inductive bias we get at the end, just boils down to some RKHS. So it's just all some big kernel machine, some big SVM or some big kernel ridge regression. And did we really need to like develop deep learning just in order to do kernel ridge regression? I mean, I know we can just do kernel ridge regression, or do kernel SVMs, or kernelized perceptron. Okay, so what's going on here? So in order to understand, and in particular, I want to point out here that all the inductive biases that we had before, nuclear norm, sparsity in the frequency domain, this the second order total variations, all of these are not RKHSs. Okay? Either they're not norms at all, okay? Or maybe they're norms, but they're norms that I know are not an RKHS. Okay? So in particular, I know that I will not be able to explain those inductive biases with a tangent kernel view. Okay? So it seems that there is some disconnect here. Okay? So let's see actually what's going on. So in order to understand it, let's understand when do we enter the kernel regime. So we're going to focus here on, for simplicity, on homogeneous homogeneous models of some order. In particular, if you think of ReLU networks without skip connections, you get homogeneity with the order that corresponds to the depth. And we're going to look at some loss. We're looking at the dynamics, and again, we're going to look at infinitesimal step size, so just the gradient flow dynamics. It's a gradient descent with infinitesimal step size, initialized to some W naught, but we're going to look at different scalings of the initialization. So we're going to see what happens when you change the scale of the initialization. Okay? And so I'm going to denote W alpha infinity is if I train my model with infinitesimal gradient descent or gradient flow, initialized at scale alpha, then I'm going to train it. I'm going to get to a zero error solution eventually because I'm over-parameterized. Which zero error solution do I get to? W alpha infinity is what is the zero error solution I get to. So this is what I actually get with gradient descent among all the different global minima. Okay, so what can we say? So at least for the squared loss, what Chizat and Bak showed is for any model, doesn't matter its width, doesn't matter if it's a neural network or not, for any homogeneous model at least, if I take this initialization to infinity, then I'm going to enter the kernel regime. So if I take the initialization to infinity, then the entire optimization trajectory is going to approach the optimization trajectory of just kernelized gradient descent with the kernel given by the initialization. Okay? So that means that I approach the kernel regime as the scale of initialization goes to infinity. And in that case, indeed, I will get the inductive bias I'll get just corresponds to an RKHS. Okay, the RKHS given by the initialization. Okay. And now we get back to this important question that somebody in the back there asked, which is, how does the scale of initialization affect the results I showed before? So all the results I showed before in one way or another rely on the scale of initialization being small. So in particular, this metrics factorization result, it was written explicitly in the slide, and I think somebody noticed it, which is good, is only valid when the initialization goes to zero. Okay? So, and then when initialization goes to zero, I get all these rich non-RKHS's behavior. Okay? And I claim that this is really where I want to be. Because again, if all I'm doing is an RKHS, I don't want to do deep learning. The whole interesting thing to me is, how can deep learning do stuff that is not an RKHS? Okay? RKHS I already know how to do. Okay? Okay, and it seems here the scale of initialization plays a very important role. So let's try to see it specifically. So what we want to understand is, how do we move just by changing the scale of initialization from these very rich things like sparsely inducing biases to something which is as boring as an RKHS? Okay? So in order to understand that, what we're going to look at is the simplest possible model that has this phenomena of moving from a rich regime to an RKHS in an interesting way. And this model is just, you can think of it as linear prediction with square parameterization. So all we're going to do is linear prediction, okay? Linear regression. Okay? So we're going to do linear regression. So our predictor is just going to be beta times x, but we're going to parameterize this beta instead of using beta, using the square root of the coefficient. So our parameters are going to be w, and the coefficients are going to be w squared. Okay? With the caveat, I'm actually going to have, instead of just w squared, I'm going to have w plus squared minus w minus squared. Okay, so I'm looking at the difference. I'm doing this for two reasons. One is I want to be able to get both negative and positive coefficients. So W plus squared captures the positive part and W minus squared captures the negative part. Otherwise, beta would be non-negative. And the second reason is I want to be able to scale the initialization without exploding my predictions. So if I have a model like this and I initialize all the W pluses and W minuses to be constant, all of them to be alpha, so I'm only going to be at initialization, I'm going to look at just initialize everything to alpha, then my predictor initialization is always going to be 0. Okay, because every coefficient is going to be alpha squared minus alpha squared. So this way I can scale the scale of parameters without exploding my predictions. Okay, so another way, so the easiest way to think about it is just linear prediction with square parameterization. If you really want to, since everything these days you have to draw as a neural network, you can also draw this as a neural network. This is this very fancy neural network. It's a two-layer network with linear activations, where you just multiply each thing by two things here, one of them positive, one of them negative. If you're like me and you think of everything as matrix factorization, because everything really is matrix factorization, you can also think of this as matrix factorization with diagonal observations. Okay, where you have these observations with diagonal, and you have this both x and negative x. Okay, but anyway, this is the model we're going to look at. And what we're going to ask is, what happens when you train this model with gradient descent, or gradient flow actually, gradient descent with infinitesimal step size, and take it to infinity. Okay, you're going to reach some point beta infinity. This beta infinity will actually have 0 error, so it's going to be a perfect linear predictor, but we're only interested in this overparameterized case where the dimensionality of x is much, much bigger than the number of examples. So there are many 0 error solutions. Okay, which 0 solutions we're going to get to as a function of alpha. Okay, and what are the results from the previous slides showing us? So if I take alpha to infinity, I'm going to be in the kernel regime. And it's pretty easy to work out what the tangent kernel initialization is. It turns out that tangent kernel initialization here is going to be a scaling of the standard inner product kernel, just the standard product, which means that all I'm doing is finding the minimum norm solution in the standard Euclidean norm. So just minimum Euclidean norm solution. Okay? And on the other hand, what happens when alpha goes to 0? So when alpha goes to 0, this is actually a special case, as we said, it's a special case of matrix factorization. And so I'm going to find this minimum nuclear norm solution, just a vector case, just minimum L1 norm solution. Okay? So I see here in the two extremes here, same model, same optimization algorithm. All I did is change the scale of initialization. I get two very, very different inductive biases. Okay? And I would argue that this inductive bias is in some sense much more structured. It's sparsely inducing. It can, in many cases, be good, even though the minimum L2 norm solution could be bad. Okay, but the question we're going to ask is how does this happen? How do we transition between them? What happens if when I change alpha? Okay, can I characterize the inductive bias for any finite alpha, not only in these two extremes? And the answer is I can. Okay, I'm going to commit suicide here. Ferdinand is like looking at me like I'm crazy, and he's right. And we're going to try to show how to derive this, and we try to be quick here, but give you the general gist. So we have this model, and what we're going to look at is we're going to look at these dynamics, the gradient flow dynamics in this model. So one thing I can do, it's just pretty straightforward. Details here are less important. I can write down the dynamics in terms of beta. Okay, so just from there, in terms of W, I can write the dynamics of beta, and I get and actually partially solve this differential equation, and I get this beta. I can write it. What I did here is got essentially an integral equation. So I can write beta t as this expression that involves an integral over the residual as a time t that in turn depend on beta. Okay, believe me, I can do that. What does that give me? I can't actually solve this, but what this means is that at any time, the solution has this form for some integral over this RT. So just call S this integral over the residuals. Okay? And what I can say is that when I follow these dynamics, I stay on the manifold, on a m-dimensional manifold. M is number of observations. That looks like this. It's parameterized by S and looks like this. Okay, in particular, what is this function? It actually has a name. It's just the hyperbolic sign of the data times S. Okay, so this is similar if you're doing gradient descent on linear regression. Gradient descent with respect to beta, you always stay on the manifold spanned by the data. So it's a flat m-dimensional manifold. Now we're doing gradient descent instead of on respect to beta, with respect to W, that I also stay on the m-dimensional manifold, but it's some curved m-dimensional manifold given by the hyperbolic sign. Okay, good. So in particular, this is true for any beta. It's also true for beta at infinity. What else do I know about beta at infinity? I know that I'm going to reach the global minima, so I'm going to solve my system of equations. Okay? So these two equations, so what I have here is I have an m-dimensional manifold here and m additional constraints here. So actually, these two conditions together exactly tell me what beta alpha is. But how can I characterize it? So how can I say what this beta alpha is? So what we're going to do is we're going to say, okay, let's assume that it actually minimizes some implied regularizar. And let's try to figure out what this implied regularizar is. Okay? So we're assuming what we get is actually the minimum Q solution for our linear system. And we're going to try to figure out, is there some Q such that the minimum Q solution corresponds to these conditions? Okay, so we have here our optimization problem. We just take the KKT conditions. The KKT conditions are given by these two equations. And now we want to match the conditions on the right with the KKT conditions of this problem on the left. Okay, so great. The bottom one we already have, x beta equals y. So now we just need to match this top condition. Okay, it's an m. Both of these are a set of, give a solution space of size m. Okay? Okay, so how can we do that? It kind of looks the same. All I need to do really is take that expression, instead of writing beta as a function of s, I want to write s as, beta as a function of x transpose s, write x transpose s as a function of beta. So I just need to invert the hyperbolic sign. And now we see that this really looks the same. Okay, all I need to do is match the gradient of q with the hyperbolic sign. Okay, so all I get is a differential equation. It's very simple. All I need to do really is integrate here. So what I get is q is just the integral of the inverse of the hyperbolic sign. Okay? Luckily, I actually know what the integral of the inverse of the hyperbolic sign is. I mean, I don't, but Mathematica does. And you get this crazy expression there. Okay? Okay, so that's great. So what we worked out here is now exactly, and the important thing is what we did here is we didn't have to guess anything. We just derived it. Okay? We just calculated it. Okay? And we see exactly for any finite initialization what I get. I get this minimum Q alpha solution, and I can tell you exactly what this Q alpha is. Okay? So let's look at this. This is a function Q. So what I get is this minimum Q alpha, or Q alpha is component-wise. I apply a function Q to my coefficient divided by alpha squared. So remember, alpha squared is my scale of initialization, but let's see how does it change things here. If I initialize very large, alpha goes to infinity, then that means that I'm only going to care about the function Q on very, very small arguments. We're very, very close to 0. Okay? And about 0, this function Q is quadratic. Okay? And so what I get is a quadratic penalty on each coefficient. I get autoregularization. Okay? If, on the other hand, alpha is very, very small, I only care about the function Q infinitely far away from the origin. And in infinitely far away from the origin, this function becomes almost linear, close enough to linear that I actually do get L1 regularization in the limit. So now we see how we transition from L1 regularization to L2 regularization. Okay, and we can see the entire transition. In particular, we can also ask questions like, for example, how close do we need, how small or how large does alpha have to be to actually approximate L1 and L2? Okay? And we can answer these questions. We can say that to approximate the L2, then alpha doesn't have to be that large at all. It only has to be polynomially large in how well we want to approximate the L2. But if you want to approximate the L1 norm, then actually alpha has to be tiny. Okay? Alpha, if I want to get an epsilon approximation for the L1 norm, then alpha has to be exponentially small in both how well we want to approximate and the dimensionality. Okay? So we do get the L1 norm at the limit, but we really have to do tiny initialization. Okay, okay, and so let's see. Okay, I'm not gonna get to logistic regression. I'm sorry, we're done. Okay, so let's see how this plays out in terms of learning. Okay, so let's look at a specific learning. So now, up until now, there's nothing about learning here. This is just optimization, right? I get any x and y, the x and y are deterministic, and I'm asking you just what will happen if I do gradient flow and the squared loss for x and y using this model. But now let's see how this plays out in a learning problem. So let's suppose that you have a sparse regression problem. Okay, so really y is equal to some beta star xi, where beta star is sparse. Okay, so now as I change alpha, I go from L1 regularization to L2 regularization. So I can see this in the right. This is kind of how well I'm approximating each one as I change alpha. And indeed, that translates into better learning or worse learning, because I know that for a sparse regression problem in high dimensions here, reasonably high, 1,000 dimensions, doing L2 regularization doesn't help me at all. I'm not going to get anything. So if alpha is large, I don't get any learning at all. When alpha is small, then I approximate the L1 norm and I do get learning. Okay. Now, the interesting part is to ask, okay, so which alpha should I use? So in this case, if suppose I do have a sparse regression problem, and I insist on just training it by doing unregularized gradient flow on my square parameterization model. Which alpha should I use? Which? What? Small. So small? Use small. So right, I want to use small alpha because a large alpha I'm not going to be able to learn. So should I take really alpha to be extremely small? Because remember that to approximate the L1 norm, I have to take alpha very, very, very small. Okay? So do I want to take alpha really close to 0? Do I? Who thinks I should take alpha really close to 0? Okay. Who thinks maybe I don't want to take alpha very close to 0? Why not?
Numerical issues.
Right. So alpha equals 0 is a saddle point. Okay? Alpha equals 0, I initialize all the parameters to 0, and it's the same as metrics factorization, I'm not going to move. If I take alpha to be extremely small, I'm going to be super close to a saddle point. It's going to take me forever to actually escape that saddle point. So I cannot take alpha to be small. So actually, what alpha do I want to use? I'm not going to take alpha that's close to 0. I'm going to take alpha. So I said that I need to get really approximate L1 norm. I need to take alpha that's roughly exponentially small. Well, exponentially small in 1,000. So e to the negative 1,000. Okay, I'm definitely not going to take it that small. Rather, I'm going to take it moderate. I'm going to take alpha somewhere over here. Because if I take alpha somewhere over here, I still succeed in learning. I still get good error, but my optimization problem is much easier. Okay? So this suggests that because of this very slow, the way I approach L1 very, very slowly, the right regime to use is not necessarily this rich regime, but maybe some intermediate regime. It's interesting to understand that. Okay? That somewhere, there's just on the edge before the kernel regime. Okay? And in particular, I think that this is, I'm going to end soon, but this is one of my favorite experiments. We can ask the following. So for every, let's actually go back here. So for here, there's suppose I want to get some target error. I want to get 1% error. Okay? Which alpha should I use? I should use the largest alpha that allows me to get 1% error, because then the optimization would be more sufficient. I can ask now, how does this change when I have more and more samples? Okay? So this is what we did here. We asked, 2.5% error. Okay? We asked, as a function of the same sparse regression problem, as I increase the amount of data, how small do I need to initialize? Okay, or how large am I allowed to initialize? So this dashed line is the informational limit. Okay? Over here, I can do it, okay, in this case, but I'd have to take alpha to 0. Again, it's going to be very, very difficult. Okay? I can't actually numerically do it. But once I have more samples, I can be a bit more relaxed in terms of how well I'm approximating the L1 norm. And now I can see that I can take larger and larger alpha. And once I have, like, say, a factor of 30% more samples or something like that, which I would say is reasonably moderate, 40, maybe 50% more, then now I can actually start taking values of alpha which are pretty decent, like 0.01 or something like that, which is very kind of a reasonable scale of initialization. Okay, not 10 to the negative 700. Okay. Now note that at that point I'm doing something that's fairly different from the L1 norm. I'm minimizing this Q alpha norm, which is fairly different from the L1 norm, but it's still very different from an RKHS, and it's still sufficient for learning. An L2 norm would not work here at all, even with this amount of data. Remember, we have 1,000 dimensions. Even if I have 100 examples, minimizing the L2 norm is not going to get me anywhere. Okay, I think I'm going to have to end here. Let me just say that I'm not going to talk about all these things, but using the same methodology, you can also ask, how do the other parameters actually affect being in this kernel regime or rich regime? Okay, so and before as a form of summary, I say that my general view of I hope in the first part I convince you that really the important thing is what is the implicit bias of the algorithm, and from my perspective, the whole challenge of understanding deep learning is understanding what can deep learning do that linear models or kernel methods cannot do. because the whole point is going beyond kernel methods. And that's not so easy. Many of the results that we have so far, the positive results in deep learning, only show that using by training a deep network, we can learn something that we can also learn using a kernel. And that's boring. What I want to understand is it really possible to learn with deep learning things we cannot learn using a kernel? And we saw today examples, we have hope for that, because, for example, I can learn approximately low rank matrices, which I provably cannot using a kernel. Okay? And in order to do that, we necessarily have to escape the kernel regime. As long as if we're only studying neural nets through the tangent kernel, we cannot possibly go outside what we can do with an RKHS. And so what I'm interested in is understanding how do we transition between this kernel regime and how do we exit it. And I talked about the scale initialization. That's just a starting point. We can also talk about other parameters that affect, help me escape the kernel regime, like adding depth, adding width, talking also about optimization accuracy, step size, batch size, and other issues. Okay, I think I'm going to end here. It's exactly an hour and 10 minutes. Okay. And I'll take more questions. Thank you.
So I have collected some questions
Sure.
from Canvas. So it's here. Can you
Okay.
answer?
Okay.
Only two because we don't.
Okay. Answer two questions. So answer these two questions?
Yeah.
Okay, good. So the first question is a very good question. What happens if instead of doing two-layer matrix factorization, instead of writing W as U times V, I write it as a deeper matrix factorization. I write W as U1 times U2 times U3 times U4 times U5. Or I think the question just asked about U1 times U2 times U3. How do things change? That's a great question, and it turns out to not be so easy. And that depends on on one thing. It depends on the loss function that you use, and it turns out that there's a huge difference here. And this is what Verdun wanted me to talk about, and unfortunately I did not have time, about whether you use the squared loss or something like a logistic loss or cross entropy loss. So if you use the logistic loss or cross entropy loss, then at least in the limit, then the deeper the factorization, the sparser the bias would be. Okay? The surprising thing is, and this was pointed out by Nadav Cohen, Sanjeev Arora, and co-authors, I apologize, I don't remember the name of all the co-authors, is that if with a squared loss, at least in the cases we can prove something, like for, actually I have this, okay, sorry, I have the results here. So then at the limit of initialization goes to 0, no matter how deep you are, you still get the nuclear norm. Even if you're depth 7 or depth 12, depth 1 you get Frobenius norm, depth 2 you get the nuclear norm, and any further depth you still get the nuclear norm. This was actually extremely surprising to me when they found that out. Now, does that mean that the depth doesn't matter at all when you go, if you talk about the squared norm? It turns out it does, because even though as alpha goes to 0, maybe I'll just show, I actually do have some, see the next slide is exactly about this. So it does. So it turns out it does matter. What happens is the limit as alpha goes to 0 is the same. Again, at least in the cases we can prove, which are these commutative cases or diagonal cases. But the way you approach it is different. In particular, one thing is you approach it much, much faster. If we said that for depth 2, you approach L1 norm or nuclear norm, but extremely slowly. You approach it logarithmically slow. So for higher depth, you approach it much faster. You approach it polynomially. What we're seeing here is we're looking here, each curve corresponds to a different depth. Okay? And we're looking here at a measure of are we closer to L1 or to L2. Okay? So the way we're looking at it is just the ratio between the norm of a sparse vector and the norm of a dense vector. For L1 it's the same, and for L2 it's the same. For L1 there's a big difference. So with depth 2 we get this curve. And trust me, eventually, if you go, I don't know, like all the way to Oregon or something like that, then it will actually eventually behave like L1. But you have to go to Oregon. Okay? If you look at any other depth, then it goes to L1 much, much faster. Okay? And the deeper you are, it goes to L1 faster. So that's one thing that's happening. But it turns out, it seems that also you get empirically better performance with higher depth. Empirically, you get performance that's better than with a nuclear norm. We don't understand why. And this plot is a bit misleading because when I say that they approach L1 slower and faster, that's only part of the thing. They approach it from different directions. This plot is very misleading because it reduces the whole complexity of the implicit regularizer to a one-dimensional thing. Are you closer to L1 or L2? But really, all of these, if each one of these curves is an implied regularizer for a different depth, approach L1 from a different direction. And as we said before, since the relevant regime seems to be not deep inside the rich regime, but just in the transition, so I'm somewhere here maybe, each one of these points is very different. It approaches L1 from a different direction, and it seems empirically that the deeper ones have in some sense a better inductive bias, and we don't understand this. Okay? Okay, so this is the first question, and if you want to read more about this, there's a paper by, where is it? This paper by Aurora, Cohen, Hu, and Lu that talks about deep matrix factorization. In our paper that is not cited here, and then we have a paper that is an archive where we also study this for diagonal problems as a function of alpha. Okay, the second and last problem. I really like the idea of why we care about the neural architecture, not due to the feasibility of training, but the geometry it induces over functions. Could we do the reverse? If we have some kind of desired geometry, is there any method to design a parameterization or optimization procedure to induce the geometry we want? So I think this goes back to a question also somebody asked here. Maybe. We try to do this a bit by saying, so to some extent, you do a bit. If, for example, at least if you're working with a logistic loss and you want to minimize some norm, then you can do steepest ascent with respect to that norm, and then the implied regularizer would correspond to the max margin solution, at least relative to that norm. So would relate to that norm. The question is, why exactly would you want to do that? So again, if you already, and maybe it does make sense in some cases, but I think designing things from scratch, if you already know, and this goes back to what I think Trevor mentioned, somebody else here, if you already know what is the desired bias you want, what is the desired regularizer, just put it in there, just minimize it directly. Okay? But rather what we're trying to figure out here is what is the inductive bias that we get out of here, and what we can maybe do is change the optimization procedure maybe to get something more similar to what we want. But I think doing it completely from scratch, maybe we could do it, but then maybe we can do it also other ways. So I think those are...
Yeah. I guess we can take one more quick question from the audience.
Yes?
Question about the noisy regime. So in all cases, it's
The noisy regime?
noisy regime, like you have x beta equals y, this is what you study. And what happens if I have noise?
Note that here I have, I do have noise in here. So there's two, okay, so it goes back a bit. In all these cases, I'm studying noisy situations in the sense that reality is noisy. The true labels are noisy. So in these sparse regression problems, here I'm showing, this is the same plot I showed before of how alpha has to be in order to get it. I'm just showing it also for different depth. And again, I'm going to hijack your question to show that with more depth, I can initialize much more reasonable values and still get reconstruction. Note that the model here is noisy. I do add noise to yi. Okay, quite a bit of noise actually. The training though is done with what we now call interpolation learning. So I do insist on a zero error solution. I can do that because I'm way over parameterized. Then even if my labels are noisy, I can still get a zero training error solution. Okay. So this is a noisy case. Why am I getting a zero training error solution and not a solution that allows for some noise? If that was the question, or what happens if I mean.
My question was basically on that in the analysis, I saw that you have always the quality.
Right, because we're looking at this is not assuming that data is noiseless, but rather insisting on interpolation learning. And insisting on zero training error. Even though I'm noisy, I'm still insisting on zero training error. Okay? If I don't insist on zero training error, then the situation is more complex in various ways. But the thing is that this does match what seems to be happening in reality, that we are frequently training to zero training error. Okay. Sorry, we're done.